winner of the Nobel Prize in Physics in 2006. Start off and design the website, the University Venture website that you've been looking at. He started this whole program, the Cosmology workshop.
Right. So I actually encourage students, undergraduate students, to do the work, and here we've encouraged teachers and outstanding high school students to do the work. So part of the important thing is to learn how to get people to want to do something exciting and different.
And speaking of learning, something that you had said at the opening of the BCCP a few years ago, that I think a little bit's been lost in science, that hopefully we'll be getting back to, is that science used to be, you could get funding to test something out, and it was okay if it failed. And I thought that was a real important concept in science, is that we learn from our mistakes as well as from what goes right. And I guess a lot of funding nowadays doesn't always fund things that aren't sort of a sure bet, which is a sad thing, because I think some of the creativity and some of the kind of serendipitous discoveries get lost if we don't have the permission to try things out, and we get them right, we get them wrong, we learn either way.
It was very important. You saw that here at LBL, which is a premier research institution. In the best days when the funding was strong, there was a very strong push by the senior management to let young people take risks and try things out, and if they failed, they only got trouble about failing if they didn't put it aside and start something new and succeed at that. That you were expected to fail, but you weren't supposed to hold on and try and make it work if it wasn't going to work. You want to try things and show either that it's going to fail in a clear way or show that it's going to succeed in a clear way. Those were the choices. And you saw the same thing in the heyday of Silicon Valley, when the venture capitals would give people startup money, and if they succeeded, great, because they really made a lot of money. If they failed, they weren't just to come back and ask for more money unless they could prove they were going to go. They had to actually start some new company. And so several of my students and postdocs actually started companies and succeeded and sold their companies. And one of them made a film called The Inside Job as a result of that, which is about how the financial industry doesn't do that anymore. So it's not the issue of failing. It's not that we want you to fail. You do learn when you fail. It's just we want you to be clear about trying things, taking risks, and then recognizing when you should try something else. And it has to do with, I think, one of the philosophies about doing science, and this goes back to my advisors, that you really should have something in mind when you do an experiment. There are people who want to do these theory or model independent experiments, and that's generally a good idea, but in general you want to have some framework or some idea that you test against the observations, but be willing to give that up. Don't be so wedded to that idea. It's the same thing about if you're trying something and it fails, and you see it fails in a spectacular way, and it's not your fault, it just fails because it fails, then you've got to try something else. And the same thing is true of theories. You try an experiment. If the theory is overruled, you have to pick a new observations. And what science is about is doing that in a way to take your human prejudice out of the situation. The fact that you love the theory because it's so beautiful, or you love this technique, or because you invented it, or whatever. You have to be willing to go on and do the next thing. So that's what we're hearing about. And no place is the rigor for doing this kind of thing greater than it is in high energy physics, because there's a long tradition. So my job was actually to welcome you here. I would have welcomed you yesterday, but I was on an airplane yesterday. But also to introduce Lauren Tomkins. And I get to do this because I have to apologize to her every time I see her, because I'm the one that talked her into working on the LHC, saying this is going to be exciting, this is going to be historic, and you'll be really glad to do this instead of one of the other projects you're doing. Only it took
a few extra years.
And so, but fortunately she has a job waiting as soon as she finishes up here. But she's one of the outstanding graduate students we've had here at Berkeley, and we're sorry to have her leave, except we're glad to have her go to New Jersey. So Lauren's going to tell you about the LHC experience.
Thank you very much. Yeah, so I've been at Berkeley for a very, very long time because I was also an undergrad here. So I started as an undergrad in 2000 and then stayed on for grad school. And we can talk a little bit more about that later, but I just finished my PhD, and as George said, we'll be finally moving on. I'll be very sad to leave this wonderful place. You don't really get views of, you know, the bay like you do anywhere else, so it'll be hard to leave. But what I'm going to talk to you today is about the LHC Atlas, which is the experiment that LBL is involved in and its connection to 21st century cosmology. So throughout the talk, please ask me questions whenever you like. Don't feel shy about interrupting me. I gave a talk 2 years ago at this workshop, and I was very, very impressed by the questions, so please impress me again. So the first thing I'm going to try to explain in this talk is why we're talking about particle physics at a cosmology workshop. And then I'll go into specifically what the LHC is and what it plans to do, and that in fact what we are doing right now. And then I will go through how collider detectors work to show you what the experimental aspect is of particle physics. So let's start by comparing particle physics and cosmology. So here, particle physics is always going to be we, because that's my background. But so we have a standard model. So a picture right here is made up of fundamental particles, which I'll go through in more detail in a minute. Cosmologists also have a standard model. They believe they know the way they know what the components of the universe is. They may not know specifically what they are, but they can at least classify them. We are interested in the fundamental truths of nature. We're interested in how fundamental particles interact and what are the laws that govern these interactions. And they are also interested in the fundamental truths of nature, how the universe evolved, why it is the way it is, etc. And then there's a whole lot that we don't understand. So this plot kind of encapsulates the state of where particle physics is right now. On the y-axis is just a probability. So the high part of it is very low probability. The 0 is high probability. And then the x-axis is the Higgs boson mass. And I'll talk about the Higgs boson mass in a minute, but you've probably heard that word before. And in any case, what this says is that we think the Higgs boson should be at this mass, but all this yellow part has been excluded. Meaning that we haven't seen it yet, and so where it's most likely to be found, we haven't seen it. There's also a lot that they don't understand. So this is, oh gosh, it's a little bit, the axis is a little bit, sorry, fuzzy, but this is billions of years from today, and then this is the average redshift, and you can see these are the observations that they've made of supernova, and you can see that they don't know if the universe is expanding. George, maybe you can tell me which way the curve goes.
It's curving up. The universe is expanding
It's
faster
expanding
and
faster. Yes. Anyways, there's a lot that they don't understand in this plot either. But there are a lot of differences too. So we here in particle physics are interested in the smallest scales of matter. We're interested in quarks, so much smaller than quarks, and that's a distance scale of 10 to the minus 19 meters. They are interested in the largest scale of matter. The scales of the universe is greater than 10 to the 24 meters. Another big difference is that we run experiments. So we collide protons together in a lab and observe. But they make observations because you can't recreate the universe over and over again. And so there are some fundamental differences, but really, oh, sorry. Forgot. They're searching for dark energy. I'm sure you guys have heard about it, or maybe this is too early on in the workshop. You guys heard about dark energy? Yes. Okay. So everybody's trying to figure out what it is, but I found some on the internet. You can buy dark energy in 16-ounce bottles. Yeah. And so now you guys, Cosmology, can do experiments as well with this. But seriously, we are asking the same question, just coming at it from very different scales, and that is, how does the universe work? Because at both the larger scales and the smaller scales are, in fact, very connected. All right, so now we're going to go through a particle physics crash course. So I mentioned previously the Standard Model. I think you guys have maybe read a little bit about that already. Yes? No? Maybe the charts, okay. So the fundamental particles can be divided up into sort of three different subclasses. There's quarks, leptons, and the force carriers. And so quarks, there's three generations of quarks, and there are two stable quarks, which are the up and the down quark. And these are what make up protons and neutrons. So they're what we call, they're the sort of ordinary matter that we see every day. Then there are leptons. These are electrons, and then there is a particle called the muon, which is the heavy version of the electron, and it's what we call semi-stable. It lives long enough that we can observe it. And so those are sort of the particles that we interact with on a daily basis. Then there are the neutrinos. You guys heard about neutrinos? Yeah? They're kind of an exciting thing to study. They are particles which carry no electric charge, and they don't really interact with anything. So they're considered to be kind of ghostly particles. So they're also stable, and we observe them by not observing anything quite often. And then there are the forces. So we'll go through the different forces. First, there's electromagnetism, E&M. You guys are probably quite familiar with that at this point. Then there is the weak nuclear force, and this is what governs radioactive decay. This is mediated by the W and Z bosons. Have you guys heard of the W and Z bosons? Did that come across in your charts? Yeah, so they're special particles. They're a lot like the photon, which is the carrier of the electromagnetic force, very similar. However, they're heavy. They've got mass. And so they don't live very long and they decay. So what you can see here is we have the down going to up. So this is a neutron going to a proton, and the down emits a W particle, it becomes an up, and then the W decays to an electron and an electron neutrino. So what we have is that these W and Z bosons, since they don't live very long, they decay, and so the Z boson can go to 2 muons or 2 electrons. And the W bosons can go to a muon and a neutrino, or electron and a neutrino here. And these will become important later because these are what we look for in our detectors. We look for the signs of the W and Z by looking at the muons or electrons. Does anybody have any questions at this point? Yeah? Oh, that means 2 muons. So the important thing about the Z boson is that it has 0 electric charge. So when it decays, it needs to decay to 2 charged things with opposite charge, a plus and a minus, and that's why it's 2. The W, however, does have charge. It's got charge either plus or minus, and so it usually goes to a neutrino that has no charge, and then an electron or a muon, which does have charge. Any other questions?
Alright, so that looks like a muon and a muon. I mean, if they have opposite, if they're going the opposite direction. I mean, it sounds like a muon and a muon. That's sort of negative.
So this is they can be a positive or negative muon. Right. So each of the muons and electrons have both charges.
It's like a muon and an anti-muon.
Exactly. Muon and antimuon, or electron, anti-electron, or we call it positron. Any other questions? No? Okay. So then there is the strong force. And this is the force that binds together nuclei. So it makes the ups and the downs stick together to form the protons and the neutrons, and it also makes the protons and the neutrons stick together to form the nuclei. And it's called the strong force because it is, in fact, the strongest force that we have. We have the strong force, the weak force, and then the electricity, magnetism, and that's their relative strengths. And then there's the Higgs boson, which you guys have probably heard about, right? It's the mysterious particle that we're searching for at the LHC. And it's really a kind of fuzzy mystery particle that gives other particles mass. And I'll go over this in a little bit more detail in a few minutes. But it basically, it's the sort of the keystone to the Standard Model. So we observe that particles have mass, but we don't know why. And they can't have mass unless there's something like the Higgs boson. And without this Higgs boson, the Standard Model is really incomplete. So the primary goal of the LHC is to find the Higgs boson or the Higgs mechanism, whatever gives particles mass. So let's go through the Higgs. So it's a big problem in particle physics. Why do particles have mass? And so there's some very clever ideas came up. Peter Higgs, a guy named Peter Higgs, and a few other people came up with a clever solution to this. So what you postulate is that the universe is filled with a Higgs particle condensate. So you can imagine just that there are Higgs particles condensed everywhere in the room. And then when a particle is traversing through space, how strongly the particle interacts with this condensate determines its mass. And so here we can see an electron is a pretty light particle. And so if it were to be traveling through this Higgs mass, it would interact only very rarely. And how often it interacted would determine its mass. The neutrino has almost no mass, pretty much zero mass, and so it would go along and it wouldn't see the condensate at all except for maybe very, very rarely. And then there's something called the top quark, which is the heaviest observed particle, and it would be bumping into the Higgs condensate all the time because it's so heavy. And similarly, the force carriers also interact with this. So gravity and the electric force, photons, the graviton and the photon don't really have any mass, so they wouldn't really interact at all with the Higgs force. However, the weak force carriers, the W and Z bosons, as I said earlier, that they're heavy, they would interact with the Higgs mass, and so they would be bouncing around, or the Higgs field, and they would be bouncing around. And so what the LHC is aiming to do is to observe the Higgs boson, and we can do this if we pop a Higgs boson out of the condensate by colliding things at high enough energy. Right, so the primary, the safe, okay, let's put it this way, the sort of safe bet that the LHC is built on was, can we complete the Standard Model? We think we can in some form, so what is the origin of mass? And then the next question, which is, do we really actually live in 3 spatial dimensions and 1 time dimension? Are there more particles or symmetries that we haven't discovered? What is the nature of dark matter? As you guys have heard, that there's 25% of the energy in the universe is made up of this dark particle that we haven't created in a lab, and we don't really know anything about it other than it exists and that it interacts via gravity. So can we create that at the LHC? And then there's even more questions, is like, why do we live in an antimatter-less universe? Why are we all made of normal matter? You'd think that when the universe was created, that equal parts of matter and antimatter were created. And there were, but then something changed that balance, and we all of a sudden live in a matter-full universe. Why are there 3 generations of matter? Just why does it stop at the top quark and then tau neutrinos? What's going on with neutrinos? They're really bizarre particles. They don't seem to be like the other ones we have. And there's gravity, which is, we don't even really, gravity doesn't fit in. When you talk about particle physics, we don't talk about gravity because it's just so different from the rest of the forces. My favorite example is that I can hold up this pointer, right, and the entire Earth is pulling down on it, right? I mean, the way gravity works, that you'd be full, yet my little hand is able to keep it up just by electromagnetism. The friction that's in my hand keeps this up. So that just shows you that gravity is really, really, really weak. So we can't deal with that. And then we don't even think about dark energy. That's way beyond particle physics. So really what the LHC is dealing with is sort of the top half of this list of stuff. But they really are all questions that drive quantum particle physics. And as you get down, you kind of run into cosmology. So let's talk for a minute about the LHC. It sits underground, about 100 meters underground, under France and Switzerland. right near Geneva, Switzerland. Very pretty area. Protons are accelerated around a ring that's about 27 kilometers around, and they're collided at an energy of 7 TeV, trillion electron volts. So if we were to put the LHC in the Bay Area, that's oops, maybe there's a pointer here. That's where it would be. So here's San Francisco, here's the Bay, we're like right up here somewhere, something like that. So it would basically span the whole Bay Bridge if we were to have it in the Bay Area. So it's one of the world's most impressive, in my opinion, one of the world's most impressive machines. There's over 30,000 tons of magnets that are cooled to 1.7 Kelvin, and that's colder than outer space. You guys have heard of the cosmic microwave background, CMB? That's 2.7 Kelvin. Oh, as our Nobel Prize winner got some little award for. It's 1.9 Kelvin is how cold. They use superfluid helium to cool this, and they cool 27 kilometers of magnets with superfluid helium. It's an engineering feat that was really impressive. When the protons are accelerated to 3.5 TeV, they are at 99.99, there's 5 nines and 1 6% of the speed of light. There's roughly 10 to the 12 protons per beam, and there's millions of collisions per second. So the data rate is enormous. In fact, when LHC is going at full steam, it should be 1.8 gigabytes per second of data recorded, and that's hundreds of thousands of DVDs of data a year. So it's just an enormous amount of data. So really, the technological work that goes into making this happen is huge. And it also comes at a fairly high price tag. It's total cost is around $8 billion, depending upon the accounting methods. And this is funded by primarily funded by Europe, but also the significant, maybe about $500 million involvement from the US, something like that. And countries in Asia, so all over. So there's 6,000 plus scientists on Atlas, my experiment. We have 3,000 scientists. There's roughly 600 universities and 85 nationalities. So all continents, with the exception of Antarctica, have people who are involved on this. So it's a truly global endeavor, I think, unlike what you can see really anywhere else. So that's one of the really exciting things about working on it, is that you are working with, some people don't like the fact that you're working with 3,000 other people, but it's also very exciting to be working with 3,000 other people from all over the world, best minds. It's a lot of fun. So as I mentioned, so we asked, why did we build this $8 billion machine? And as I've mentioned before, the primary goal is to find the Higgs boson, and we know we'll do it some way or another. So there's 2 experiments that were designed to find this. There's Atlas, my experiment. There's the LHC, which is our cross-ring rival. There's a healthy rivalry there, but we have friends on the other experiment too. Then it is the case to search for new physics, what happens beyond the standard model, and all the LHC experiments are going to do this. We might find the dark matter particle. We don't have to find it, but hopefully we will. That would give us a lot of insight into dark matter. Then there's an experiment called LHCb, which is designed to understand the origin of the baryon asymmetry in the universe. So this is why we live in a matter universe versus antimatter universe. And how many of you guys have heard of Angels and Demons? Did you guys see the movie? Yeah, so CERN's in that because we have an antimatter bomb or whatever. We don't have enough antimatter to do that. But it's kind of fun to see CERN in the popular media. And then also, there's an experiment called Alice, depending upon which side of the ocean you're from, and it is designed to investigate the properties of the quark gluon plasma, which is really what it was like a microsecond after the Big Bang. So oftentimes the LHC gets, they say, oh, the LHC, we're going to, Atlas or CMS, we're going to recreate the Big Bang, but it's really this experiment, Alice, which collides lead ions and gold lead and gold nuclei together. These they are really recreating what it's like seconds after the Big Bang. Yeah.
So by any chance, what they're using Atlas, CMS, what these acronyms?
Yeah, so I think Atlas has now officially, God, I almost used shrugged off, but awful. It is almost, I think we've officially gotten rid of it being an acronym. So it was a toroidal LHC apparatus, which is a terrible, they just wanted to call it Atlas and they came up with an acronym. CMS is compact muon solenoid. So that's because CMS is this very, very compact, enormous magnet and everything, a solenoidal magnet and everything fits inside of it. So they are much more, Atlas is by far the biggest experiment, but CMS is the densest.
Muon,
Huh?
is that muons? Muons running through it or something?
Yeah, so it's the muon system. So actually both, it's funny, both Atlas and CMS, the muon system, so the toroidal part of Atlas is also its muon system. So I'll go through that in a minute, but it's to be able to detect muons. LHCb is just, I think LHC and then B because it looks for B quarks. And then LEAS is I think it's an LHC large ion collider or an LHC ion collider experiment or a large ion collider experiment because they're really looking at the collisions of ions, lead ions. And yeah, they definitely got the best, I think. They're cute. They have an actual Alice, as, you know, from Alice in Wonderland as their logo. So, other question? Uh-huh. Happens to the Higgs. So when matter and matter and antimatter interact, they just turn into energy. And so the Higgs doesn't directly play a part. It does, but there is it doesn't have an antimatter version of it. So it's just plain matter, so it can't annihilate. Yeah. Any other questions? Okay, so I guess this is time for the break. But this is the LHC rap, which I'll play while we're breaking. Because it does. So feel free to just stretch or whatever.
Tunnel underground, designed with mind to send protons around a circle that passes through Switzerland and France. 60 nations contribute to scientific advance. 2 beams of protons swing round through the ring they ride, filling the hearts of the detectors that makes it collide, and all that energy packed in such a tiny bit of room becomes mass particles created from the vacuum, and then LHC is where the antimatter's gone. Alice books and collisions of lead ions. CMS and Atlas are 2 of a kind. Whatever new particles make you find. The LHC accelerates the protons in the lead, and the things that it discovers will rock you in the head. We see asteroids and planets, stars galore. We know a black hole resides in each galaxy's core. But even all that matter, we cannot explain what holds all these stars together. Something else remains. The star matter interacts only through gravity, and until you catch a particle, there's no way to see. Take it back to conservation of energy, and the particles appear clear as can be. You see particles flying in jets they spray, but you notice there ain't nothing going the other way. You say my law has just been violated. That don't make sense. There's gotta be another particle to make this balance, and it might be dark matter. And for the first time, we catch a glimpse of what is from most of the known verse because CBs is where the antimatter's gone. Alice books and collisions of black ions. CMS and Atlas, they're 2 of a kind. They're looking for whatever the particles they can find. And it's sort of like matter's evil twin, because except for charge, the given is the spin, then the spin for a particle, and it's anti-separate. You can store an antiparticle on a new shell, because when it meets its normal twin, they both annihilate. Matter turns to energy, and then it dissipates. When matter is created from energy, which is exactly what they'll do in the LHC. You get matter and antimatter in equal parts, and they try to take this back to when the universe starts, the Big Bang. Back when all the matter exploded, but the amount of antimatter was somehow eroded, because when we look around, we see that matter abounds, but the antimatter's nowhere to be found. That's why. LHC is where the antimatter's gone. they ought to see it right away. And if it doesn't, the scientists will finally say there is no Higgs. We need no physics to account for why things have mass. Something in a standard model went around, but the Higgs also haven't said just what it does. They suppose the particles are mass because there is this Higgs field that extends to all space. And some particles slow down while other particles race straight through like a photon. It has no mass, it's something heavy like a clockwork. It's dragons, and the Higgs is the boson that carries the force. And the particles stay furthest from the field that is its source. They'll protect it. When LHC is where the antimatter's gone, Alice looks at collisions with the ions. CMS and Atlas are two of a kind. They're looking for whatever new particles they can find. That's why you may think that gravity is stuck, 'cause when you fall off your bicycle, until you hit the then you should take a hurt, but if you think the force is powerful, you're wrong. You see, gravity is weaker than we, and the reason why is something many scientists see. They think about dimensions, we live in just 3, but maybe there are others that are too small to see. It's into these dimensions that gravity extends. It makes us seem weaker when you're on our rack, and these dimensions are rolled up, so tight that they don't affect you in your day-to-day life. But if you were as tiny as a graviton, you could enter these dimensions and go wandering on, and they'd find you. When LHC is where the antimatter's gone, Alice looks at collisions of lead ions. CMS and Atlas are two of a kind. They're looking for whatever new particles they can find. The LHC accelerates the photons of the lead, and the things that it discovers will rock you in the head.
Oh yeah, our understanding of the universe is about to change, thanks to the Large Hadron Collider. This is C to the E to the R to the N, base ray knowledge ego. Mr. B,
Alpine cat, over and out.
Yeah. She was a science writer for Atlas. Very good. Anyways. Okay. All right, so we're going to get back and we're going to, for the second half, we're really going to talk about how particles are detected and how we, for example, would know that a Higgs boson was created at the LHC, how we're actually looking for them. So everybody knows Einstein's very famous E equals mc squared. That means energy equals mass times the speed of light squared, and essentially what we were talking about earlier, that energy is equivalent to mass, and mass is equivalent to energy, just mass is another form of energy. And so that means that if we accelerate protons to really high energy and collide them, they can turn into something new, a new particle. And so as I mentioned previously, the LHC collides millions of collisions per second, and 99.99, you know, put quite a few nines after that, of the collisions are boring. I did my thesis was on how often the boring collisions happen. For real. I have had to wait several years for the LHC, so I wanted to do something where I didn't have to wait for the 1 in a billion collisions to write my thesis. I went for the one, the collision that happened every time. But then, and everything once in a while, something interesting is created. So what we have here are 2 pictures of protons colliding, and we can see inside of them is our little quarks and gluons, so the pieces of the proton, and they're gonna collide. But as you can imagine, we have protons, right, and they're made up of 3 quarks, right, each. And they're bound up by the strong force, so they're bound up by gluons. And so when they collide, you have only some probability of maybe one quark interacts with another quark, or maybe a gluon interacts with a quark. So you're not colliding like billiard balls, right? You're colliding big stacks of, junk. And so we see something that's really messy that comes out. You see a big mess. And so what we have to do is what we really want is we want something like this. There are 2 protons come in. They make a Higgs. The Higgs decays to 2 Z bosons. And then the Z boson decays to 2 electrons. One of the Z bosons decays to 2 electrons, the other one decays to 2 muons. And that's what we want. But we have to find that out of this. And so that's the real challenge in experimental particle physics, and that's what we're going to talk about. So the other thing we want is Higgs going to 2, is another thing is Higgs going to 2 W's, which is now what I'm looking for, not the sort of 1 in a 10 billion event rather than the... So Higgs goes to 2Z bosons, and then each goes decays to 1 decays to 2 electrons, and 1 decays to 2 muons. Okay. And this is the same thing, but instead of 2 Z bosons, it decays to 2 W bosons. And so since the W's have the electric charge, they decay to 1 electron and 1 neutrino, or 1 muon and 1 neutrino. So the rest of what we're going to talk about is how do we reconstruct something like this? How do we read in our big detector into this? So this is just going to be some units and definite. I'm going to be saying things like electron volts and things like that. So I just wanted to go over some of the units and definitions and useful numbers. So in particle physics, we were operating this very convenient system where basically all constants, like the speed of light, are set to 1, which is very nice. And so you never have to worry about remembering what the speed of light is or something. And energy is then measured in something that we call electron volts. An electron volt is the amount of kinetic energy gained by an electron when it accelerates through 1 volt, a potential difference of 1 volt. It's just an electron volt, it's just a unit of energy. That's the way we think about it. And just to give you an idea of the scale, 1 electron volt is about 1.6 times 10 to the minus 19 joules. So very small unit of energy. To give you some reference, an electron is about half of a MeV, it's a million electron volts. A proton is about 1 billion electron volts. The Z boson is 91 billion electron volts. So there's this great, nice quote by Richard Feynman who says, "A single atom is such a small thing to talk about that its energy in joules would be ridiculous to talk about, inconvenient. But instead of taking a definite system like a definite unit in the same system, like 10 to 20 joules, physicists have unfortunately chosen arbitrarily a funny unit called the electron volt. I'm sorry we do it, but that's the way it is for physicists." So it's a funny thing, but you just get used, just remember it's a unit of energy. All right. Okay, so particle detection 101. So this is going to be the toy detector that we're going to talk about, and it all shows the sort of basics of how particles are detected. So we'll start with the beam pipe. That's the part in the center. So there's a pipe running down throughout the whole LHC, which the protons are accelerated, and then they're collided in here in this beam pipe. And then around the beam pipe, most detectors have a tracking chamber. And so I'll go into more detail about each of these in a little bit, but a tracking chamber reconstructs the traces of charged particles. And so here we have a muon, which is traversed through the tracking chamber. And then there's other charged particles here. But there's a photon and a neutron, and these are neutral particles, and so they don't leave tracks in the tracking chamber. Outside is the magnetic coil because since these are charged particles, when they're put in a magnetic field, they'll curve. And so that we try to curve them and help us measure their momentum. Outside of that, in this red, is an electromagnetic calorimeter. So this measures the energy of things like electrons and photons, electromagnetic energy. Outside of that, in the green, is the hadronic calorimeter. So this measures the properties of hadrons, which are basically particles that are made up of quarks. So like a neutron is made up of quarks, and a proton is made up of quarks. There's other particles such as these things called pions, which are made out of quarks. But basically anything that interacts via the strong force, interacts primarily via the strong force, gets detected in the green part, hadron calorimeter. There's another magnet, and then the furthest outside are the muon systems, the blue here. And that's because muons don't interact very much. They only interact a little bit, so they can make it all the way out of the detector make it all the way out to these layers of the detector without losing their energy. Then there's also the neutrinos. So the neutrino here is drawn as a dashed line because it doesn't leave any signature in the detector. So the way it's usually detected is through momentum imbalance. So imagine that, there's conservation of momentum, right? Which you guys probably learned in mechanics. And so ignore everything but this proton, and ignore everything but the proton. If all we saw were the proton, then we'd see something coming out this way and nothing to balance it on the other side. And so we know that there had to have been a neutrino on the other side because we need the conservation of momentum to form. So this is the sort of, and so what I'm going to do now is I'm going to show you how in Atlas each of these layers are implemented. But particle detectors are really generally created like this. They're kind of like an onion shell, or onion, layers of an onion is generally how they're described. So here's Atlas. To give you a scale, this is a person right here. So it is 40 meters long and 25 meters tall. I've been down in the cavern. I mean, Atlas has been sealed up and you can't go down there now, but I've been down there when it was just built, and it's like, they call it like a cathedral underground, and it really is because it's such an amazingly huge machine. And so here in the innermost part are our tracking chambers, this yellow and this red. Then outside this gold and the green are our calorimeters, the electromagnetic calorimeter and the hadronic calorimeter. And then this huge outer system, which takes up about, I think, over 50% of the volume, is the muon system. So it's made of these orange pieces, which are magnets. So it's a big toroidal magnet. And then the blue parts, which are the muon chambers, which are the places, yeah?
For just the idea of this detector, you mentioned that particles are stopped by each layer of the magnet. Maybe the signature. What is the signature?
So we'll go through that in a minute. And each one is different for each different type of detector. Right. So let's go. We can go straight to the tracking chambers. So the way the tracking works is that charged particles pass through some sort of detecting medium, and they knock electrons out of the medium. So for example, here is through probably a piece of silicon, and so the charged particle goes through, it like knocks the electrons out of the atoms, and then there's an electric field applied, and then these are read out. So that's how it's read out. And this is usually something like silicon, kind of like CCDs in your camera, like your digital camera. And then also sometimes we use gas. It's another detection method. And then what happens is you can reconstruct tracks by, so the charged particle passes through, the electrons are read out, and then it creates a little hit in the detector. And then what we have is, the tracking detector will have its own little set of layers. So in this little toy example, there's 3 different layers, and so there'll be hits in each one of these layers. And then since we put this in a magnetic field, the tracks will bend, the particles will bend. And then we can reconstruct, I mean, it's just essentially connecting the dots. So we connect the dots, and we know that a particle went through this path here. And then we know, based on the curvature, what its momentum was. And then that gives us a measure of its energy. So that's how a tracking detector works. This is the pictures of Atlas's detectors. So this is the pixel detector. It's the innermost. And actually, this right here, this part right here, that's the pixel detector. It was built here at LBL. This part of it was built here at LBL. A little bit before I started working with the Atlas group. But it's basically these little parts here are little silicon sensors, just like in your digital cameras. And so when a particle travels through it, it just creates a hit, and we read it out. And so here it's being installed. This guy is an LBL guy. That was a former LBL postdoc there. It's really the heart of the detector. Then there's something called, there's another set of tracking, another layer out here. This is called the silicon, the SCT, semiconductor tracker. And then there's something made out of gas tubes. The outside, that's the TRT. And so when we have a collision, it looks like this. This is how we visualize the collisions. So in here there are 3 layers. Yeah, 3 layers of the of the detector, and so each one of these colored lines is a track. And you can see the little hits. So this is the innermost, the pixels, the pixel area. This is what we call the strip area, and this is the TRT. So that's how charged particle tracks are reconstructed. Yeah. Uh-huh. Yeah.
Can you tell what charge it is by which way it curves?
Exactly. That's very important in some cases. We really do want to know if it's positive or negative.
And you it can also detect momentum. That means the curve would be a little more straighter if it had more momentum.
Exactly. Exactly. So higher energy or higher momentum tracks look very straight to us, and that's what we want to find is we need to know momentum. You have a question? No. Is that okay? Yeah. So let's talk about calorimeters now. So calorimeters measure, as I said, the total energy of the particles. So electron, photons, and something called jets, which we'll talk about in a minute. And so what you do, the principle of calorimetry is you stick a really dense material in front of the particle, and then and so the particle interacts a lot with the material, and then the energy is read out. So for example, what Atlas uses is we use sheets of lead and then a material called liquid argon, which is the noble gas, liquid argon. And so the electron comes in. Here the lead is the black accordion shape, and then the gas is where the liquid argon is. And so an electron comes in, and then it starts to interact with the material, and then it creates a cascade of interactions. So the electron interacts with something in the lead, that produces more electrons, they interact, and so the whole thing showers and gets rid of all its energy in here. So so you get these big cascades, is what happens in calorimeters, and then you measure the total energy that's produced here. Atlas calorimeters, there's two different types. There's the electromagnetic, which is the lead. It uses lead and liquid argon, and it's in this funny accordion shape so that we can detect, so that there's no gaps where the particles could go where there wouldn't be lead. And then there's something called a tile calorimeter, which is sheets of steel and then something called a plastic scintillator. So it's just a piece of plastic. Did you guys do the cosmic ray experiment? Okay, so tomorrow what you're going to do is you're going to use the scintillator, which is a plastic. When a charged particle goes through it, it creates light. And so that's what we use here also. That we use the same thing in Atlas, in the electromagnetic. And so then when electron goes through, it deposits energy, and the green here is this calorimeter, and the red is this. These are just different pieces of it. And so we see, this is exactly what you were asking. This is what we'd see. We'd see a big spike of green or yellow, it's the same thing. And that's what we end up measuring. Yeah, it would tell us, this tells how this looks, tells us that it's an electron. Yeah, the entire thing, like how wide it is, how much energy is, that sort of all gets characterized into what an electron is. So this has like the shapes of this, you can see it's divided up here into little pieces. So we measure how much energy is in one and how much energy is on the side, things like that, and to tell it's an electron. And then lastly, there's the muons. So the muons are the only particles which can escape the full detector except for the neutrino. And so they're the only ones that reach out into this outer layer. And so basically what we do is we stick more tracking detectors, but really far away. So they're just, this is Atlas's muon system. It's enormous. It has lots of different types of technologies. But basically all you have to do is if you know something gets out that far, that you know it's a muon, because everything else will have already interacted. So these are pictures of Atlas's muon system. This is the end caps. I mean, this is going to be like 20 meters tall. These are the magnets. You can see there's a person right there, people standing here. And these, like, it's hard to tell, but these are like the muon chambers here, these big chambers. This is another one here. And so when you get a muon produced in a collision, these pictures I'm showing you are all real data. These are real collisions. This here muon's produced and it hits in these chambers, and so you can reconstruct. We see, oh, something must have passed through these three chambers. They're all lit up, and so we reconstruct it like that. Any questions? And so then there's one more object. So I've talked about the muons and the electrons and the tracks. There's one more thing that we have, which are called jets. And there's this property of quarks that they can't be produced alone. So when you produce two quarks here, produce two C quarks, what happens is they will start to fly away from each other, but what will happen is a new set of quarks will pop out from the vacuum in between them and make a new pair. And so this is continually happening. So what happens is when you make when you produce a quark, you actually produce a spray of quarks. And we call these jets. And so here what you see is like the quarks are made and then they turn into particles and then it deposits energy in a calorimeter. So generally when we see quarks, what we see is when we see quarks, is what we see is a big a lot of tracks and then deposits in the electromagnetic calorimeter and deposits in the hadronic calorimeter. Yeah? So this is the other thing that we look at. So let's just we can put together the different building blocks of the events, and we have jets, we have muons, we have the electrons, and we have tracks. And so what we're going to do now is we're going to go through actual events and try to determine what happened. Oh, first we're going to watch a little movie. So here we're in the LHC tunnel, passing through the border between France and Switzerland. And then we're coming to Atlas. This is on our way. This is collision hall. And so the two protons meet, they collide through the tracker here. These green parts, that's the electromagnetic calorimeter, and the yellow parts is the hadronic calorimeter. What you can see here is tracks, and then we see the sprays of green here. So it happens created and then positive. This is the make it was created. So we're just going to look at pictures like this for now. So first we're going to start with this one. This is one taken in October 2010, May, so a little over a year ago. So this is the view that we were looking at previously, right? This is the end-on view. So here's the tracker of the different layers. This is the electromagnetic calorimeter, and here's the hadronic calorimeter. And this is the same thing, but looking at it from the opposite plane, right? So the protons are coming in here, they're colliding right there. And this is the 3D view that we were talking about, the 3D information. So this is just, all of this information is compressed onto this one piece. And so what we see here is we see some sprays in the electromagnetic calorimeter here. And so that tells us that these are 2 electrons. And this is just another view of what the energy that's in the calorimeter. I'm going to ignore it. But so basically what we see 2 tracks, and we see deposits in the electromagnetic calorimeter. And that is exactly what we saw, which is the Z going to an electron, going to 2 electrons. So here's another one. This is a little different view. I wanted to show you all real events, but the problem is that the people who like to make pictures of muons use one visualization program, and the people who like to make pictures of electrons use a different one, and so I can't show you a unified version of both electrons and muons. But here what you can see is you can see a muon, because you see these hits out in the outer muon system, and then we see a dashed line, and that means that there's missing energy. So what do you guys think this is? It's muon and missing energy, which we know, yes. So what do we think that it made? What do you think created these? Any guesses? It was created from a proton, but I see what you're saying. Almost, but what's the intermediate particle? It's a W boson, actually. It's from so when a proton emits an electron and turns into a neutron, it's got a W boson involved. But yeah, so what we have here is a W boson going to the muon chain. This one was taken in April of 2012, or 10, sorry. And so this tells us that the energy of one of the muons was 40 GeV, the missing energy is 41 GeV, and then the mass was around the W mass. Yeah?
So I think the discovery of the W is this hugely big deal.
In the 80s.
When I was
Yeah. Yeah.
So now it's just like, oh, it's working, the machine is working. We're just
Yeah. Yeah. No, it's pretty funny because the LHC is going to be so high luminosity that at CERB, when it, 5 years from now, when it's running really at full steam, they'll make one of these, like, you won't, so at this point we can save, like, we can record every one of these, right? But there'll be so many of them that we won't be able to look at all of them eventually. It's kind of crazy. So, what do you guys see in this one? Somebody want to tell me what they see? Yes, jets, exactly. So how many, so we've got one going here. It's kind of, you can tell it's color coded. There's one here. There's a purple one here, green, blue. So what you end up having, in here you can see it in the other view. So what's happening here is you have 8 jets, so 8 quarks that are being produced at the same time, which is pretty cool. That's a lot of things happening at once in the detector. This one is also very special because you see that here that there's a lot of tracks, right? There's a lot of tracks. This is zoomed in on this view here, and you can see that we actually have 7 protons interacting at the same time. So here's one, here's another, there's another, there's another. And so what we can do is with this tracking detector, we can reconstruct where the charged particles came from. And we're finding that we have 7 interacting at the same time, which is a lot. So here's another one. This one is hopefully labeled. You've got 2 muons, an electron, and then missing energy. So what do you guys think was produced here? I heard something. There's a Z, definitely. There's just more than just a Z, though. There's something else. Any other guesses? So what made the Z? The 2 muons, right? So what do you have left? You have the electron and missing energy. So this is then, this is the missing neutrino, this is the missing ET is a neutrino. And then the neutrino plus the electron make, yes, W boson. All right, so here what we have is both the W and the Z are produced. The Z goes to 2 muons, the neutrino, the W goes to neutrino plus the electron. And so if this had been 2 W's or 2 Z's, it might have been a Higgs boson, but unfortunately we don't have any pictures of that. And this was in October of last year. So this is not a real event, this is a simulated event. But what do you see here? You see, oh, it's kind of hard to tell. There's 2 muons here. And then this is actually 2 electrons, and I'm sorry, it doesn't, I don't have much choice in which one we get, but it's 2 electrons. And so this is what a Higgs would look like, actually, if we saw one. So here's the Higgs is produced, it creates 2 Z's. One goes to 2 muons, it's this one here, and the other, oh sorry, these are the 2 electrons. They went in the same direction, I'm sorry. This blue stuff here is the 2 electrons. This is a jet, actually. So this is what we're hoping to see. We're hoping to see enough of these that we know that we have the Higgs. Haven't seen it yet, but. So what do you think is going on here? What do you see in this picture? This is the muon. It's the same thing. It's just the view is a little different. So everything is in sort of its natural size. So what's going on? Muons? Yeah. There's tons of hits in the muon detectors here. They're all over the place. And what this is actually, it's a cosmic ray air shower event. So it's not an LHC collision. What happens is that, this is some artist rendition, is that a particle comes in from the upper atmosphere, it interacts with something, and then it makes a huge shower, and then we see it in Atlas. And so tomorrow you guys are going to build detectors to look for cosmic rays. So you'll look for these guys, but you probably won't. These showers are very rare, so you won't detect those, but you will detect actual cosmic rays. This is what a big air shower looks like in Atlas. Yeah?
So do you have some way of looking at Atlas?
Yes, we do. So part of it is that these happen randomly in time, and the collisions happen at fixed times. So primarily, it's just based off of that. There's also, each one of the hits that we get in the detector has timing information. So we know if the first hit was here or here. So if it comes, yeah, so if it comes from up here, we know. But these are pretty, yeah, spectacular events. So this is a kind of funny one. It kind of looks like an event with just a lot of jets, right? I mean, it looks like there's bunches of quarks being produced in here. This is an old simulation. What it is what a black hole would look like in Atlas. So if we created a black hole, what would happen is, rather than destroy the Earth, like some guy in Hawaii thought that we would destroy the Earth. Did you guys hear about this? Yeah, right. We can make them. In fact, this morning, one of the postdocs at LBL is looking for black holes, and he gave a talk this morning, and he hasn't seen them yet, but there are people actively looking for them, and this is what they look like. They look like a huge spray of particles in all directions. So just a word about those black holes. We can create them. And it's just as simple because black holes are created when there's a really high energy density, right? That's what happens with stars. Get a really high energy density, black hole is created. Well, we are creating a really high energy density when we collide two protons together. But black holes do something, they can't actually destroy the Earth because they're not stable. So they radiate and they decay away. And we know that they won't looking through astrophysics. So this is another connection between particle physics and cosmology. We can tell because we would have created them in cosmic rays, so there'd be black holes going through the Earth all the time if they were stable. And also we look and we see that there's lots of neutron stars, and neutron stars would also create black holes. And so we know that we won't create deadly black holes in the LHC. We hope we create actual black holes because that would be a really cool new physics signature. But
They should be really, really tiny black holes.
Yeah.
I mean, do they even...
They last for
microseconds, right?
yeah, even less. Yeah, no, they decay immediately. So you can see them by their products, but they won't destroy anything. And so there's this convenient website for keeping track of whether or not the Earth is being destroyed. Go there. All right, so conclusions. So basically what I hope to get across today is that particle physics and cosmology are really trying to answer the same types of questions, but from very different angles. Very powerful and complex machines such as the LHC are really needed and necessary to investigate the smallest pieces of the universe. And it's been quite a rocky start, as the LHC was supposed to start in 2008. It didn't get started until end of 2009. But the data is flowing in faster than we could have dreamed. It's quite amazing. So in the next few years, the LHC will hopefully enrich our understanding of the fundamental interactions of nature. We'll know whether or not we have a Higgs, and hopefully there's much more beyond that. That's it.
Things out, and if they failed, they only got trouble about failing if they didn't put it aside and start something new and succeed at that. That you were expected to fail, but you weren't supposed to hold on and try and make it work if it wasn't going to work. You want to try things and show either that it's going to fail in a clear way or show that it's going to succeed in a clear way. Those were the choices. And you saw the same thing in the heyday of Silicon Valley, when the venture capitals will give people startup money, and if they succeeded, great, because everybody made a lot of money. If they failed, they weren't just to come back and ask for more money unless they could prove they were going to go. They had to actually start some new company. And so several of my students and postdocs actually started companies and succeeded and sold their companies. And one of them made a film called The Inside Job as a result of that, which is about how the financial industry doesn't do that anymore. So it's not the issue of failing. It's not that we want you to fail. You do learn when you fail. It's just we want you to be clear about trying things, taking risks, and then recognizing when you should try something else. And it has to do with, I think, one of the philosophies about doing science, and this goes back to my advisors, that you really should have something in mind when you do an experiment. There are people who want to do these theory or model-independent experiments, and that's generally a good idea, but in general you want to have some framework or some idea that you test against the observations, but be willing to give that up. Don't be so wedded to that idea. It's the same thing about if you're trying something and it fails, and you see it fails in a spectacular way, and it's not your fault. It just fails because it fails.
Finally, moving on, it'd be very sad to leave this wonderful place. You don't really get views of, the bay like you do anywhere else, so it would be hard to leave. But what I'm going to talk to you today is about the LHC Atlas, which is the experiment that LBL is involved and its connection to 21st century cosmology. So throughout the talk, please ask me questions whenever you like. Don't feel shy about interrupting me. I gave a talk 2 years ago at this workshop, and I was very, very impressed by the questions, so please impress me again. So the first thing I'm going to try to explain in this talk is why we're talking about particle physics at a cosmology workshop. And then I'll go into specifically what the LHC is and what it plans to do, and that in fact what we are doing right now. And then I will go through how collider detectors work to show you what the experimental aspect is of particle physics. So let's start by comparing particle physics and cosmology. So here, particle physics is always going to be we, because that's my background. But so we have a standard model. So a picture right here is made up of fundamental particles, which I'll go through in more detail in a minute. Cosmologists also have a standard model. They believe they know the way they know what the components of the universe is. They may not know specifically what they are, but they can at least classify them. We are interested in the fundamental truths of nature. We're interested in how fundamental particles interact and what are the laws that govern.
Then you've got to try something else, and the same thing is true of theories. You try an experiment. If the theory is overruled, you have to pick a new observations. And what science is about is doing that in a way to take your human prejudice out of the situation. The fact that you love the theory because it's so beautiful, or you love this technique, or because you invented it, or whatever. You have to be willing to go on and do the next thing. So that's what we're hearing about. And no place is the rigor for doing this kind of thing greater than it is in high geophysics, because it's just long tradition. So my job was actually to welcome you here. I would have welcomed you yesterday, but I was on an airplane yesterday. But also to introduce Lauren Tomkins. And I get to do this because I have to apologize to her every time I see her, because I'm the one that talked her into working on the LHC, saying this is going to be exciting, this is going to be historic, and you'll be really glad to do this instead of one of the other projects you're doing. Only it took
A few extra years.
And so, but fortunately she has a job waiting as soon as she finishes up here. But she's one of the outstanding graduate students we've had here at Berkeley, and we're sorry to have her leave, except we're glad to have her go to New Jersey. So Lauren's going to tell you about the LHC experience.
Thank you very much. So I've been at Berkeley for a very, very long time because I was also an undergrad here. So I started as an undergrad in 2000 and then stayed on for grad school. And we can talk a little bit more about that later, but I just finished my PhD, and as George said, we'll be.
George Smoot, winner of the Nobel Prize in Physics in 2006. Helped start off and design the website, the University Venture website that you've been looking at. He started this whole program, the Cosmology Workshop.
Right. So I actually encourage students, undergraduate students, to do the work, and here we've encouraged teachers and outstanding high school students to do the work. So part of the important thing is to learn how to get people to want to do something exciting and different.
And speaking of learning, something that you had said at the opening of the BCCP a few years ago, that I think a little bit's been lost in science, that hopefully we'll be getting back to, is that science used to be, you could get funding to test something out, and it was okay if it failed. And I thought that was a real important concept in science, is that we learn from our mistakes as well as from what goes right. And I guess a lot of funding nowadays doesn't always fund things that aren't sort of a sure bet, which is a sad thing, because I think some of the creativity and some of the kind of serendipitous discoveries get lost if we don't have the permission to try things out, and we get them right, we get them wrong, we learn either way.
It was very important. You saw that here at LBL, which is a premier research institution. In the best days when the funding was strong, there was a very strong push by the senior management to let young people take risks and try.
These interactions. And they are also interested in the fundamental truths of nature, how the universe evolved, why it is the way it is, etc. And then there's a whole lot that we don't understand. So this plot kind of encapsulates the state of where particle physics is right now. On the y-axis is just a probability. So the high part of it is very low probability. The 0 is high probability. And then the x-axis is the Higgs mass, Higgs boson mass. And I'll talk about the Higgs boson mass in a minute, but you've probably heard that word before. And in any case, what this says is that we think the Higgs boson should be at this mass, but all this yellow part has been excluded, meaning that we haven't seen it yet. And so where it's most likely to be found, we haven't seen it. There's also a lot that they don't understand. So this is, oh gosh, it's a little bit, the axis is a little bit, fuzzy, but this is billions of years from today, and then this is the average redshift, and you can see these are the observations that they've made of supernova, and you can see that they don't know if the universe is expanding. George, maybe you can tell me which way the curve goes.
It's curving up. The universe is expanding
It's
faster and
expanding
faster.
faster, yes. Anyways, there's a lot that they don't understand in this plot either. But there are a lot of differences too. So we here in particle physics are interested in the smallest scales of matter. We're interested in quarks, so much smaller than quarks, and that's a distance scale of 10 to the minus